Welcome to Science Listener. Tonight, your eyes drift beyond the familiar curve of the Milky Way. The stars seem endless, but hidden among them is something greater, a faint smudge of light in the constellation of Andromeda. To the naked eye, it looks like nothing more than a blurred cloud, soft and unremarkable. Yet behind that blur lies an entire galaxy, the closest spiral neighbour to our own. 2.5 million light-years away, Andromeda stretches across space with 1 trillion suns, more than twice the number in the Milky Way. Its spiral arms weave through dust and gas, its heart burns with ancient stars, and far around it swarm small companion galaxies like satellites caught in its gravity. What you see as a blur is in fact a vast island universe, drifting slowly toward us. For centuries people called it a nebula, a mystery cloud. Only in the last 100 years did we learn the truth. It is another galaxy, immense and alive, bound to us by gravity. And someday, billions of years from now, the Milky Way and Andromeda will meet, colliding and merging into one. In this journey, we'll step into Andromeda piece by piece, from the faint glow that first caught human eyes in the night sky, to the clusters of stars, the hidden black hole at its centre, and the ocean of dark matter that surrounds it. It is both familiar and alien, a mirror of our own galaxy, and a reminder that we're not alone in the vast architecture of the cosmos. Close your eyes and picture it. A hazy oval stretching 6 times wider than the full moon, silver light soft against the darkness. It hangs quietly above the horizon, waiting. And in that quiet you realize the universe is larger, richer, and more connected than it first appears. And this is where our story begins. Far beyond that quiet haze hidden inside the faint oval of light lies a secret that reshapes the destiny of the night sky. Andromeda is not still. It drifts toward us, carrying the weight of billions of years, its motions silent yet unstoppable. To the eye it looks harmless, a soft smear above the tree line, no brighter than a modest star. Yet astronomers have tracked it with careful instruments and learned that it approaches at 301 kilometers per second. Every tick of a clock pulls it a little nearer. That is more than 1 million kilometers each hour, silent, constant, unstoppable. The movement reveals itself not through sound or tremor but through light. When the glow of Andromeda is broken down in a spectrograph, the thin black lines that mark the elements bend toward the blue. Almost all distant galaxies show the opposite, a redshift, their light stretched as the fabric of the universe expands. Andromeda is the rare exception, its light squeezed, waves shortened, the fingerprint of an approach. In 1912, at the Lowell Observatory in Arizona, Vesto Melvin Slipher made that first measurement. He pointed his spectrograph at what was then called the Great Andromeda Nebula, and the line slid not toward red but toward blue. The nebula was not floating away, it was closing in. This discovery unsettled the old order. In those years, many still thought Andromeda was part of the Milky Way, just a cloud inside our own galaxy. Yet the speed that Slipher recorded was impossible if it were so close. The only explanation was distance, vast distance. Andromeda had to be an entire system of stars, a world of its own. His numbers whispered of something larger, something that changed the scale of the universe itself. The truth grew clearer in the 1920s, when Edwin Hubble used Cepheid variable stars in Andromeda to calculate its distance. They were far beyond the Milky Way, proving the nebula was not a nearby wisp, but another galaxy altogether, a spiral rivaling our own. Combined with Slipher's measurement, the picture sharpened. This immense island universe was not stationary. It was heading for us. Think of the night you step outside in autumn when the air carries the smell of wood smoke and damp leaves. The stars seem frozen. No sense of motion touches your skin. Yet above you, that pale oval slips closer. 1 trillion suns locked into a slow collision course with the very home you stand on. The silence hides the truth. The galaxy is on the move. Generations after Slipher and Hubble, new instruments refined the numbers. The Hubble Space Telescope, launched in 1990, confirmed the blue shift and mapped Andromeda's motion with even greater accuracy. Later, the Gaia spacecraft added details of tangential movement, the sideways drift that might alter the final meeting. But the forward rush remains, steady as ever, about 301 kilometers per second, written into every ray of light. You do not feel the pull, but it is there. Gravity has already chosen the path. The Milky Way and Andromeda are partners bound in a long orbit, spiraling together through the local group. The meeting will not be tomorrow, nor in 1,000 years, but on the scale of galaxies the future is near. In about 4 billion years, the two spirals will merge. The sky above your distant descendants will no longer hold a faint oval. It will blaze with the light of two galaxies intertwined. For now it waits as a blur, a quiet smear of silver. Yet every hour it grows a little closer. Every year shortens the gap by millions of kilometers. The universe is not static. It is restless, moving, drawing one great system of stars toward another. And in that restlessness lies the unavoidable future. When the two spirals finally meet, the sky will not split with fire but unfold in silence. Galaxies do not collide like stones on a road. They pass through each other like ghosts, their stars separated by light years, their halos brushing long before their hearts converge. From Earth, the first sign will not be destruction but spectacle. The oval of Andromeda will swell across the night, no longer a faint smear but a rising giant, its arms stretching wider than the moon ever dared. The first contact will happen in the halos, those vast invisible envelopes of hot gas and dark matter that reach hundreds of thousands of light years beyond the disks. Long before a single star crosses paths, the halos will merge, shock waves of gas heating, streams of material pulling into new shapes. If you were alive in that distant age, you would see the night sky grow crowded. The arc of Andromeda would bloom until it rivaled the Milky Way's own band, two great rivers of stars crossing each other, tangled like threads of light. Computer simulations run in the 21st century, using the power of supercomputers at NASA and ESA, have shown how it will unfold. Around 3.9 to 4.5 billion years from now, the first pass will draw the spirals through one another. Stars will not smash together. The emptiness between them is too vast. Instead, gravity will stretch both galaxies, bending their arms into long tails, streams of stars flung outward like sparks from a wheel. Entire solar systems will be carried into new orbits, some hurled into the dark outskirts, others drawn toward the newborn center. In those models, the night sky of Earth becomes a theatre. One evening, Andromeda fills half the heavens, its spiral arms glowing like silver smoke. Then the Milky Way and Andromeda overlap, two disks interlaced, a luminous chaos spanning horizon to horizon. For billions of years, the two galaxies will dance this way, passing, pulling back, then falling together again, their shapes twisted and reshaped by tidal forces. The collision is not a single strike, but a long choreography. The most striking part is the silence. No roar, no explosion audible across space, only the slow drift of stars through gravity's web. The violence is in scale, not in sound. Gas clouds may crash and ignite bursts of new star formation, lighting nurseries of blue-white giants across the merging disks. Supernovae will follow, blazing briefly before fading. But on the human scale, standing on the ground, you would only see light moving, arms stretching, galaxies becoming one. The future sky holds no promise of safety, but neither does it guarantee ruin. Our solar system may survive the encounter, carried into a new orbit around the merged core, or it may be flung to the far edge, left drifting in the outskirts of a new massive galaxy. The physics is certain, but the fate of this one small star and its planets is uncertain, hidden inside billions of possible orbits. After countless passes and long tides of distortion, the spirals will no longer be spirals. Their arms will stretch into streams, their disks torn and reshaped, until what remains is no longer two galaxies but one. The Milky Way will not survive as itself. It will be consumed into something new. Astronomers call it a likely elliptical giant, a swollen sphere of stars with no graceful arms, no thin band crossing the sky. A new name has already been coined: Milkomeda, the fusion of Milky Way and Andromeda. The end of the Milky Way is not an explosion but a transformation. Once our galaxy was a thin spiral with a bright bar and arms of blue stars. After the collision, those structures will dissolve. Ellipticals are graveyards of motion. Stars still orbit, but the organized patterns are gone, replaced by random swarms. The dark lanes of dust that once traced spirals will be scattered, their gas used up in starbursts or stripped into space. What was once a graceful disk will become a featureless glow. Computer models from 2012, published by researchers using Hubble and supercomputer simulations, show the outline of this process. The first passage around 4 billion years from now will distort both galaxies into tidal tails. A second encounter, a few 100 million years later, will drag their cores closer. Finally, around 5 to 6 billion years from now, the centers will merge, and the black holes at their hearts, one in Sagittarius, a star, and one in Andromeda, will sink together, spiraling into a single monster hundreds of millions of solar masses heavy. From the ground, if Earth still orbits its star, the view will be astonishing. The organized band of the Milky Way, the sight that guided human eyes for tens of thousands of years, will fade. In its place will be a swollen oval, a hazy bulge stretching across the sky, the remnant of two galaxies folded into one. You will no longer see a river of stars overhead, but a broad cloud-like smear, bright at the center, dim at the edges, unrecognizable compared to the old sky. The scale of this change is difficult to hold. The Milky Way is 13 billion years old. For almost all that time it has spun with its arms intact, a slow wheel turning in the dark. In just a few billion more, that identity will be erased. It will not be destruction, but it will be an ending. The Milky Way as a spiral galaxy will vanish. The night sky that cradled every story, every myth, every navigation of our ancestors will be gone, replaced by the anonymous glow of a new giant. Somewhere inside that glow, the sun, if it still burns, will orbit silently, one small star among trillions. Its planets may survive, or they may be cast out. The galaxy will not care. It will have remade itself, indifferent to the memories of the creatures who once gave names to its shapes. The fate of the Milky Way is not only an end, but a reminder. Nothing in the universe stands still. The sky you see above you tonight is not permanent. It is a frame in motion, a story that keeps unfolding even when you do not notice. Every star, every cloud of gas, every galaxy is on the move, reshaping the heavens across time spans too vast for one lifetime to hold. When Vesto Slipher first measured Andromeda's blue shift in 1912, he was not just recording a number. He was uncovering the truth that our galaxy was not alone, not fixed, and not eternal. When Edwin Hubble confirmed in 1924 that Andromeda was a separate galaxy, he did more than expand the universe. He showed that even something as immense as the Milky Way had a future, a fate tied to another. These were not abstract discoveries. They were the first whispers of a coming union. Across cultures and centuries, people have looked at the Milky Way as something permanent. The bridge of souls in Greek myth, the milk spilled by Hera in ancient Greece, the pathway of spirits among the Maya. To the Norse, it is the road to Valhalla, to others a scar across the sky made by gods in anger. Yet every story assumed the band was forever. It is not. In a few billion years, it will vanish, replaced by the swollen glow of Milkomeda. The sky of myths will be erased, and a new sky will take its place. That is the reminder. You live beneath a ceiling that moves. What feels like permanence is only motion stretched across time. The constellations will twist, the galaxies will merge, and the night sky itself will change beyond recognition. The universe does not preserve what is familiar. It keeps rewriting, and yet there is beauty in that. The same physics that dooms the Milky Way as a spiral also guarantees the birth of something new. Elliptical galaxies, though stripped of graceful arms, are grand in their own way. Vast, luminous, filled with stars both old and newborn. The merger is not the end of light. It is the continuation of it in another form. If you look up tonight, the faint haze of Andromeda tells you two things at once. First, the future is written, the galaxies will merge, and what you know as the Milky Way will cease. Second, the universe is alive with change, and your small place in it is part of that same current. The blur is a messenger, a reminder that nothing is still, not even the sky itself. Long before astronomers measured its spectrum or traced its motion, people saw Andromeda as nothing more than a blur. A pale smudge above the autumn horizon, easy to miss if the night was not dark enough. To the naked eye, it has always looked fragile, a ghost of light, something you could almost rub away with your thumb if the sky were a canvas. Yet that blur is the largest object you can see without a telescope, stretching across the darkness 6 times the width of the full moon. For centuries it was noticed but not understood. In 964 CE, the Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars as a small cloud. His drawings show it as a mist, unremarkable but persistent, a patch that returned to the sky each year. Medieval stargazers, with no instruments beyond their eyes, knew it only as a curiosity. Not a star, not a planet, not a comet, just a faint patch that refused to vanish. If you step outside on a clear night far from the glow of cities, you will see it much the same way. A soft oval rising in the east in autumn, brightest near midnight, hovering in the constellation of Andromeda. It does not sparkle, it does not flicker, it simply rests there, a patient stain of silver on black. Even now, with all our telescopes and satellites, that is still how most people first meet it, as a ghostly mark your eyes are almost unsure of. The shape is real, but your vision struggles with it. Human eyes evolved to catch movement and sharp points of light, not hazy clouds. Look straight at the galaxy and it fades, lost to the cones of your retina. Look slightly to the side, and it sharpens, a trick of peripheral vision. This is why, across ages, the Andromeda Galaxy has been both obvious and elusive. Anyone can see it, but few see it clearly. It became known in Europe through Simon Marius in 1612, who described it through a telescope as like a candle shining through horn. His words captured the same paradox: bright yet blurred, obvious yet shapeless. Charles Messier added it to his catalogue in 1764, listing it as M31, not because he understood it, but because he wanted comet hunters to avoid confusing it with their prey. To Messier, it was a nuisance, a smear that could be mistaken for something else, and yet, even as a smear, it had a presence. Farmers saw it while walking home across fields. Soldiers glimpsed it in quiet watches. Travellers marked it as a faint lantern over the road. Generations lived and died under its blur, unaware they were staring at another galaxy. Tonight, if you find yourself in the countryside under a sky unspoiled by lamps, the smudge will appear just as it did 1,000 years ago. Silent, unchanging. A reminder that sometimes the greatest things in the universe do not announce themselves with brilliance, but hide as faint ghosts waiting for you to notice. That faint blur is not empty. It hides more suns than your galaxy holds, 1 trillion fires stitched into a single oval of haze. What seems fragile to the eye is, in truth, the greatest concentration of starlight you will ever see without a telescope. You tilt your head back, and the oval above you is no longer just a smudge. It is an island universe, spilling light that began its journey 2.5 million years ago. Every photon brushing your eyes tonight was born when early humans had not yet walked the Earth. The light is a messenger from an age before your kind, and it carries with it the glow of nearly 1 trillion stars. The Milky Way has perhaps half that number, its hundreds of billions dwarfed by the count in Andromeda. To call it a smudge is to ignore the immensity hidden inside it. Through telescopes, the truth becomes sharper. The haze splits into rivers of stars, knots of blue giants, swirls of gas where new suns ignite. Hubble's great images in the early 2000s mapped hundreds of millions of stars in Andromeda, creating mosaics so vast that every corner of the galaxy held clusters, nebulae, and spiraling arms. The panchromatic Hubble Andromeda Treasury, PHAT, revealed thousands of star-forming regions, each one a nursery where gas collapses into light. What the naked eye calls a blur is, in detail, the most intricate portrait of a galaxy ever made. You follow the thought further. If each of those stars hosted planets, then Andromeda could hold trillions of worlds, oceans and deserts unseen, or nothing but lifeless rock. You feel the scale pressing down. 1 trillion suns means possibilities without number, and all of it compressed into the small oval your eye calls faint. The ancients called it a cloud, and in a sense they were not wrong. It is a cloud of starlight, the glow of 1 trillion small fires carried across the void. The air around you feels colder as you think of it, not because the galaxy chills you, but because your body shivers at the idea that so much light can be so far away. You raise your gaze again, and the blur holds steady, indifferent, as if daring you to understand the weight of what it contains. Andromeda does not only hide more stars, it outweighs you. Its body of light and dark matter doubles the mass of the Milky Way, stretching farther, shining brighter, casting a longer shadow across the local group. To stand beneath it is to stand before something larger than the home you thought was everything. You grew up under the band of the Milky Way, the river of stars arcing overhead. It felt complete, like the total sky. Yet the numbers tell a different story. Andromeda's disk stretches about 200,000 light-years across, nearly twice the diameter of our galaxy. The Milky Way, measured edge to edge, spans perhaps 100,000 to 120,000 light-years, depending on how you trace its outer arms. Against Andromeda, it is the smaller sibling. The star count confirms it. The Milky Way holds roughly 400 to 500 billion stars. Andromeda may host more than 1 trillion. Imagine the difference between a crowded city and a sprawling empire. Your galaxy is vast. Andromeda is vaster still. Astronomers estimate its total mass, including the invisible halo of dark matter, at around 1.5 trillion solar masses, while the Milky Way is closer to 1 trillion. Gravity does not care about pride. The heavier body pulls with more authority. Through history, people assumed their own world, their own galaxy was central. In the early 20th century, before Hubble's discoveries, many astronomers believed the Milky Way was the whole universe. The thought that something could be bigger was unthinkable. Then the spiral nebulae were revealed as galaxies of their own, and among them Andromeda loomed close, large, and undeniably greater in weight. Overnight, the Milky Way became just one player in a larger stage, no longer the largest, not even the most massive in its own neighbourhood. The scale is humbling when you picture it. The arms of Andromeda sweep outward in long spirals filled with blue star clusters and dark lanes of dust. Each arm spans tens of thousands of light-years, containing stars younger, brighter, and hotter than most in the Milky Way's arms. Its halo of globular clusters, more than 450 known, extends far beyond the luminous disk. The largest of them, Male 2, is so massive that some scientists suspect it is the stripped core of a smaller galaxy that Andromeda devoured. The Milky Way has its swarms of globulars too, but fewer, lighter, dimmer. You feel the comparison settle like a weight. Your galaxy is impressive, but Andromeda is greater. Even the core speaks of difference. In the centre of the Milky Way lies Sagittarius A star, a black hole of about 4 million solar masses. The black hole at Andromeda's heart is at least 100 million solar masses, maybe closer to 200 million. Its nucleus is brighter, stranger, even split into the double concentration that puzzled astronomers with Hubble's sharp eyes in the 1990s. 2 glowing peaks where you expect one, evidence of complex dynamics in a core more massive than ours. Stand outside under the stars and the numbers become more than abstract. The blur above you is not just a rival, but a reminder that your galaxy is not supreme. It is smaller, lighter, dimmer in places, less crowded with suns. You live in a grand house, but your neighbour's palace overshadows it. You look up and the blur becomes heavier in your mind, pressing down with its scale, showing you how much larger the night truly is. The local group itself bends to Andromeda's size. Though both galaxies orbit their shared centre of mass, Andromeda's weight gives it dominance. The Triangulum Galaxy, M33, the third largest member, is likely bound to Andromeda rather than to the Milky Way. Dozens of dwarfs swarm around both giants, but the balance is tilted toward the heavier partner. Astronomers debate which galaxy will ultimately hold the central role when the local group collapses into one. Andromeda's claim is strong. In the end, the blur in the sky is more than faint light. It is a lesson in proportion. The Milky Way is not alone, not largest, not strongest. You stand beneath a ceiling where the neighbour outweighs your home, where the rival galaxy carries twice the stars, twice the mass, twice the glow, and in that knowledge, the smudge above you feels less like a ghost and more like a crown, one you did not know was resting there all along. Andromeda was not only a rival in size, it was the key that unlocked the truth of galaxies themselves, the moment when the universe stopped being a single home and became a vast archipelago of stars. You raise your eyes to the oval above and realize that its faint glow once split astronomy in two. Those who believed the Milky Way was the whole cosmos, and those who dared to say it was not. The clash came in 1920 at the Smithsonian Institution in Washington, D.C. It became known as the Great Debate. Harlow Shapley argued that the Milky Way was immense, containing everything: stars, nebulae, spirals, the entire universe. To him, Andromeda was only a nearby cloud inside our own system. Heber Curtis disagreed. He insisted that Andromeda was an island universe, a galaxy in its own right, far beyond the Milky Way. The two men faced off in papers, lectures, and words sharpened like blades. The audience listened, but no final verdict was reached. The night sky remained an unsettled map. The proof arrived 3 years later. In 1923, Edwin Hubble turned the Hooker telescope toward Andromeda and found Cepheid variable stars, pulsing suns whose brightness revealed their distance. The calculation shattered the Milky Way's monopoly. The stars inside Andromeda were too far away to be part of our galaxy. They belonged to another. In 1924, Hubble announced his results. Andromeda was a galaxy, and so were the other spirals scattered across the sky. The universe had multiplied overnight. You feel the weight of that revelation. For thousands of years, humans thought they lived under a single dome, the Milky Way arching like a roof. Then the faint smudge above became a doorway. Step through it, and there are billions more roofs, each with its own stars, its own dust, its own history. The night sky is no longer one house, but a city without walls, galaxies upon galaxies without end. The transformation reached beyond science. To stand beneath the blur was to stand at the edge of human imagination. Myths once said the Milky Way was milk spilled by a goddess, or a bridge of souls, or a scar left by divine fire. But Andromeda taught that the sky was not a story written for Earth alone. It was larger, stranger, more impersonal, yet more magnificent. You tilt your head back and see not just a smudge but a reminder. Your ancestors thought they knew the universe, and they were wrong. What they saw as a cloud was another galaxy. What they thought was the whole was only a part, and in that shift, the universe expanded forever. If the blur of Andromeda revealed the scale of the universe, its centre revealed its strangeness. When astronomers turned their sharpest instruments toward the core, they found not one peak of light but two, a double heart burning where only one should be. You stare into that distant nucleus through the words of scientists, and the picture is unsettling. Two bright concentrations side by side, separated by just a few light years, orbiting the same invisible gravity well. The discovery came with the clarity of the Hubble Space Telescope in the 1990s. Before Hubble, the central glow of Andromeda was only a blur inside a blur. But when its optics pierced the haze, the image sharpened into two distinct knots of light. Astronomers name them P1 and P2. P1 appeared as the brighter of the two, slightly offset, while P2 lay closer to the true centre of gravity. The expectation had always been simple: one core, one concentration, one heart. Instead, Andromeda held two. You imagine yourself in that view. The stars of P1 gathered tightly, shining like a cluster pulled off centre, while P2 hides something darker. At the position of P2 lies the supermassive black hole, unseen but dominant, the anchor of the galaxy's mass. The stars of P1 orbit it on eccentric paths, creating the illusion of a second core. But when the image first appeared on scientists' screens, it was more than an illusion, it was a challenge. The heart of Andromeda beat twice. Even now the mystery remains. Why should stars gather this way? Why two peaks instead of one? You feel the strangeness settle on your skin. The nearest giant galaxy does not even obey the simple picture drawn in textbooks. Its nucleus is not a single flame but a split, a doubled presence, a puzzle that forces astronomers to rethink how galaxies live and change. Behind the strange double glow lies something darker, heavier, invisible, the supermassive black hole that anchors Andromeda's core. You focus on the place called P2, the true centre, where gravity bends space so tightly that not even light can escape. Astronomers estimate its mass at least 100 million suns, perhaps closer to 200 million. That makes it more than 20 times heavier than the black hole at the Milky Way's heart, Sagittarius, a star. The numbers themselves are dizzying. Imagine every star you see on a clear night, then multiply that brightness by millions and reduce all of it into a single invisible point. That is the scale of Andromeda's central black hole. Its presence is inferred from the motion of stars around it. In the 1990s and 2000s, spectroscopic data revealed how stars in the core whip around at extraordinary speeds, hundreds of kilometers per second, velocities only possible if something massive and compact holds them in orbit. You stand beneath your own sky and feel the contrast. At the center of your galaxy, Sagittarius A star weighs 4 million suns. That already feels immense, a gravitational pit deep enough to shape the Milky Way. But Andromeda's core outweighs it by a factor of 20 or more. When the galaxies merge, those two monsters will spiral together, releasing energy on a scale beyond imagination, gravitational waves rippling through space-time. The black hole within Andromeda is not feeding greedily today. Unlike quasars, where black holes blaze within falling gas, Andromeda's core is relatively quiet. The accretion disk glows faintly, a low luminosity active nucleus, but it is not devouring stars with violent hunger. Instead, it waits, patient, shaping its surroundings through gravity rather than light. Astronomers describe it as a sleeping beast, immense, silent, its presence known only through the motions it imposes on others. You picture the orbits of stars near P2, each one circling a darkness it cannot see. Their paths are eccentric, some looping in close, others stretched far, a swarm held together by a single point of gravity. The double heart of P1 and P2 makes sense only with this black hole at the centre, an anchor around which the chaos arranges itself. Without it, the nucleus would dissolve. With it, the galaxy holds together, its trillion suns bound into one vast system. Even light betrays the black hole's existence. Radio and X-ray telescopes capture faint emissions from the hot gas near its edge. In the 2010s, NASA's Chandra X-ray Observatory detected flashes near the centre, signs of matter heating to millions of degrees before vanishing past the event horizon. Each flare is a reminder that the beast is alive, if quiet, still capable of feeding when material strays too close. The thought presses down as you look at the faint blur above your horizon. That oval haze is beautiful, but inside it lies a singularity that could swallow millions of suns. The contrast is almost absurd. The most delicate smear to the naked eye hides one of the heaviest objects in the nearby universe, and in the stillness of your night, you feel its pull across millions of light years, a reminder that gravity knows no distance too vast. Around that black hole, the stars do not rest. They surge in clusters, a swarm of giants, each one racing as if the galaxy's heartbeat pushed them onward. The nucleus of Andromeda is no calm lantern. It is a storm, packed with stars so close that their light bleeds together into a single glare when seen from afar. In the 1990s, Hubble's resolution first showed the crowd. Later, adaptive optics on Earth-based telescopes revealed individual points within that glare, each a star tearing along at hundreds of kilometers per second. The closer they orbit to the hidden black hole, the faster they move, obeying a law of gravity that tolerates no rebellion. The effect is dizzying, a stellar hive buzzing with energy, compressed into just a few light years across. Many of these stars are young, blue-white, massive, short-lived. They blaze hotter than the sun and will die within tens of millions of years. Their presence so near the black hole puzzled astronomers. How could fragile gas clouds survive tidal forces long enough to form them? The answer lies in bursts. When Andromeda's central regions funnel gas inward, shock and compression ignite rapid star formation, producing clusters that glow like torches near the abyss. Among them are older stars too, swollen red giants, faint dwarfs, and even variable stars whose rhythms provide clues to the density of the core. Some stars belong to the cluster called P1, the off-center concentration that creates the illusion of a double nucleus. Others whirl around P2, tighter, faster, pulled directly by the black hole. You catch the image in your mind, thousands of stars circling in eccentric paths, looping around one invisible anchor, sometimes so close they whip through perienter like stones on a sling. The swarm is not uniform. It has layers, shells, clusters within clusters. Globulars skirt the inner core while tighter groups dive into the heart, their orbits twisted, elongated, forced into harmony by gravity's grip. By the 2010s, astronomers tracked individual stellar velocities, mapping a living diagram of motion. Each line of data was another stroke in a portrait, speeds reaching 300, 400, even 500 kilometers per second, impossible without a massive black hole at the center. The swarm became proof, not only of Andromeda's weight, but of how galaxies grow, feeding on their own cores. The density is breathtaking. Within a few parsecs, the number of stars per cubic light year is thousands of times greater than in the Sun's neighborhood. Collisions between stars are rare even here, but their interactions sculpt the orbits, ejecting some, pulling others deeper. Occasional novae flare, brief signatures of stars in turmoil, lighting the crowded dark for weeks before fading back into anonymity. From Earth, none of this chaos is visible to the naked eye. The oval remains smooth, unbroken, yet telescopes reveal the turbulence beneath. Not silence, but motion. Not calm, but frenzy. The double heart of Andromeda is alive because the swarm never sleeps. Two hearts beat where one should be. The question is why? What strange mechanics twist Andromeda's nucleus into a doubled flame? Astronomers have wrestled with this puzzle since the 1990s, when Hubble first revealed the twin peaks of P1 and P2. At first glance, it looked impossible. Galaxies were supposed to have single centers, yet here was Andromeda, defying the simple model. The leading explanation is the eccentric disk hypothesis. The stars in P1 are not a separate core, but part of a disk of orbits stretched into ellipses around the black hole in P2. As those stars slow near apocenter, their light clusters together, creating the illusion of a second nucleus. Seen from Earth, it looks like a separate heart, but it is really a crowd of stars lingering at the farthest point of their loops. The illusion is a rhythm of gravity, one beat from the true center, one from the orbiting swarm. Other theories add nuance. Perhaps a past galactic merger left scars in the core, funneling stars into odd distributions. Some simulations suggest that when a smaller galaxy was swallowed a few billion years ago, its core survived long enough to seed the offset cluster. Over time, the stars spread but still mimic the shape of a second nucleus. You follow the thought further. In Andromeda's history are signs of repeated collisions, tidal streams of stars in its halo, shells and arcs that trace old mergers. The double heart may be another echo of those ancient events. The galaxy remembers in its centre what it once consumed. Still, no single answer is final. The double heart remains a mystery that resists neat closure. Data from Hubble, Keck, and simulations from the 2000s and 2010s support the eccentric disk, but anomalies remain. The brightness of P1, the precise alignment, the persistence over decades. Perhaps multiple causes overlap, or perhaps the dynamics of millions of stars near a black hole simply create patterns stranger than expected. For you, standing under the sky, the details of equations and models dissolve into a simpler truth. The smudge above is not a calm lantern, but a question without a final answer. Galaxies are not perfect machines. They carry scars, irregularities, echoes of violence, and structures that refuse to be reduced to one line of theory. The two hearts of Andromeda remind you that even the nearest giant galaxy is stranger than the textbooks promised. Beyond the double heart, Andromeda stretches outward in grace. Its spiral arms sweep across 200,000 light-years, vast rivers of stars and gas curling like brushstrokes across the dark. To the naked eye, they collapse into a haze, but telescopes reveal the structure. Long arcs of blue-white clusters, dark lanes of dust cutting through, knots of pink nebulae where new stars flare to life. The arms are not uniform. Astronomers trace at least two major arms and several fainter spurs, spiralling outward from the bar-like core. In images from the Spitzer Space Telescope and other infrared surveys, the symmetry breaks. The arms look uneven, one brighter, one more fragmented. Andromeda's beauty is not perfect geometry, but a living shape, twisted by gravity, mergers and tides. You let the image grow sharper. Star clusters glimmer like beads along the arms, each one a pocket of thousands of suns. Some are ancient, globular and red, hanging above the disk like lanterns. Others are young and hot, glowing blue, born in dense knots of gas. The arms themselves are not solid structures but waves, density waves moving through the disk, compressing clouds, igniting bursts of star formation as they pass. Seen edge-on, Andromeda's spiral is a tilted oval. Seen in detail, it is a storm of structure. Dust threads between stars, arcs bend, and the whole shape speaks of history. The galaxy has not always been calm. Past collisions left scars and the arms bear them, twisted slightly, not perfectly wound. For you, standing under the night sky, the blur hides all of this. You see only the soft oval, yet inside it are spirals stretching farther than imagination, curling in silence for billions of years. The beauty lies in the tension. A galaxy so immense that its arms can cradle 1 trillion stars, and yet to your eyes it appears as nothing more than a faint smear above the horizon. Among those spirals lies a stranger shape, a great ring of stars and gas circling Andromeda about 10 kiloparsecs from the centre. You picture it as a glowing loop stitched into the disk, a structure so clear that astronomers have debated for decades how it formed. The 10 kiloparsec ring is one of Andromeda's defining features. First revealed in detail through infrared and radio surveys in the late 20th century, it appears as a nearly circular band filled with gas clouds, dust lanes and clusters of stars. Unlike the sweeping spirals which curve outward in long arcs, the ring encircles the galaxy like the rim of a wheel. Inside it, astronomers see bursts of star formation, nurseries glowing in ultraviolet light, knots of hydrogen gas where new suns ignite. The ring is not only bright but massive. Observations suggest it contains a significant fraction of Andromeda's star-forming gas. Its diameter, about 20,000 light-years across, makes it one of the largest coherent structures in the galaxy. When imaged in the infrared by the Spitzer Space Telescope in the early 2000s, the ring stood out as a glowing circle embedded in the disk, sharp and undeniable. How did it form? One leading theory points to a collision. About 200 million years ago, astronomers suspect, Andromeda swallowed a smaller companion galaxy. The impact sent waves rippling through the disk like a stone striking water. Those waves compressed gas into a ring, igniting star formation as they spread outward. Computer simulations reproduce the pattern. A single pass of a dwarf galaxy through Andromeda's disk is enough to set off ripples that settle into a circular band. Another explanation suggests resonance. The gravitational pull of Andromeda's central bar may have funneled gas into a stable orbit, concentrating material at the 10 kiloparsec mark. Spiral galaxies often show rings linked to their bars, and Andromeda's faint bar, revealed in infrared, could be the sculptor of this loop. For you standing on Earth, the ring is invisible to the naked eye. The blur above hides it as surely as clouds hide mountains. Yet telescopes peel back the haze and show the structure glowing in false colour, pink for hydrogen, blue for ultraviolet, red for infrared dust. The circle becomes a crown around the core, a mark of both violence and order, a relic of impact or resonance that still shapes the galaxy today. The ring also hints at Andromeda's history of cannibalism. Streams of stars in its halo show that it has devoured companions before, shredding them into arcs. The 10 kiloparsec ring may be another scar of such an event, a fossil record written not in bones but in stars and dust. And if the models are right, the ripple that formed the ring is still fading, its waves echoing through the disk like a bell struck long ago. You let the thought linger. Above you hangs a blur that hides not just spirals but a ring born of collision, an aftershock still glowing millions of years later. The oval in the sky is not peaceful. It is scarred, layered, marked by history written in gas and stars. Across those graceful arms lie shadows, dark lanes of dust that cut through the starlight, carving the luminous disk with streaks of absence. To the naked eye, Andromeda is only haze, but telescopes sharpen the view. Its glowing spiral is veined with dark threads, rivers of interstellar dust that block the light of millions of suns. These dust lanes are not voids, they are matter itself, cold and dense, grains of carbon and silicates drifting in clouds, hundreds of light years thick. Under starlight they appear black, but they are the raw material of stars, the ashes of generations of suns. In Andromeda, as in the Milky Way, the lanes snake along the spiral arms, tracing their curves like ink on paper. Seen in long exposure photographs, they give the galaxy its texture, the shadows that make its beauty sharp. Astronomers in the 20th century studied these lanes with radio telescopes, tracing the 21-centimetre emission of neutral hydrogen and the millimetre glow of carbon monoxide. The patterns revealed that the dark stripes were nurseries in waiting, places where gas cooled enough to condense. The dust itself absorbs and scatters visible light, hiding young stars behind veils. Infrared telescopes from Spitzer to Herschel pierced those veils, uncovering hidden clusters glowing in warmth invisible to human eyes. You feel the irony. The same lanes that seem like scars are also wombs. Without them, galaxies would be barren, drained of fuel. With them, arms are alive, their shadows giving birth to light. When you trace those dark streaks in images of Andromeda, you're seeing the cycle of creation and destruction laid bare. In Andromeda, the dust lanes are especially prominent because of the angle of the galaxy. Its disk tilts toward us, so the shadows fall across our line of sight. Astronomers measure the tilt at about 77 degrees, enough that we see the lanes slicing across the oval like claw marks. Some are so broad that they span thousands of light years, each one a band thick with gas and dust, blotting entire swathes of the galaxy's disk. The history of those lanes stretches back billions of years. They're fed by dying stars, red giants shedding their outer layers, supernovae scattering heavy elements, collisions stirring clouds into chaos. Dust is the residue of stellar life, recycled endlessly. In Andromeda, as in the Milky Way, every lane is a record of death that becomes birth. For you, standing under the real sky, none of this is visible. The blur shows no shadow. And yet the darkness is there, hidden inside the smear, an invisible architecture that sculpts what you cannot see. The galaxy is not smooth. It is veined, scarred, streaked with the material that makes future suns. The haze above you is quiet, but inside it, dust lanes coil like rivers of night, carrying the promise of stars yet unborn. Out of those rivers of dust come nurseries, vast clouds where gravity takes hold, collapsing the dark into clusters of newborn stars. You picture the inside of Andromeda's arms not as silence but as workshops, places where gas folds upon itself until the pressure ignites fire. Astronomers trace these nurseries in glowing H2 regions, pink and red patches where ultraviolet light from newborn giants ionizes the surrounding hydrogen. Images from Hubble and ground-based telescopes reveal them as knots scattered through the arms, each one tens or hundreds of light years across. The most famous in Andromeda is NGC 206, a star cloud so immense it could be seen even in early photographs from the 19th century. Within it are thousands of young hot stars no older than a few million years, their light washing the surrounding gas in a crimson glow. The process is relentless. Cold molecular clouds collapse under their own weight, fragment into dense clumps, and in the centre of each clump a protostar forms. As material rains inward, heat rises until nuclear fusion begins. A new sun is born. Multiply this by thousands, and you have the nurseries of Andromeda. Entire clusters lit almost at once, like sparks leaping across kindling. Radio telescopes mapping carbon monoxide outline the skeletons of these molecular clouds, while infrared observatories pierce the dust to reveal the hidden infant still swaddled in gas. Herschel, Spitzer, and later missions showed that Andromeda's arms are not static. They are factories, always birthing, always shaping. You lean into the thought. Every faint point in the blur above could hold a cradle. Somewhere inside those arms, stars younger than humanity itself are already burning, and others are just now forming in cocoons invisible to your eyes. The hazy oval you see is not only ancient light, it is also the glow of a galaxy in constant renewal, stars dying and stars being born in the same breath. The cycle ties back to dust. Supernovae seed heavy elements, winds from dying giants spread carbon and oxygen, and clouds gather the debris. What seems like loss becomes material for creation. In Andromeda, this recycling stretches on without pause. Each nursery is proof that galaxies are not frozen structures but living systems, their arms both cemeteries and maternity wards. From Earth, you cannot see NGC 206 or the smaller knots of star formation with bare eyes. You see only the smear, yet knowing what lies inside transforms that smear. It is not an empty haze, it is 1 trillion suns plus countless more in the making, fire still hidden in dust, waiting to break out. Beyond the spirals and the bright nurseries, Andromeda carries fainter shapes, ghostly streams of stars stretched across its halo, the remnants of galaxies it has already consumed. You focus on the images from wide-field surveys, and the blur of Andromeda is no longer a clean oval. Around it, faint arcs and loops drift like pale smoke, tidal streams unravelling through the dark. These streams are not illusions. They are stellar rivers, thousands of light-years long, composed of stars torn from smaller galaxies as Andromeda's gravity ripped them apart. Astronomers began tracing them in the 1990s with photographic plates, and in the 2000s deep surveys like the Sloan Digital Sky Survey and later Pan-STARRS revealed their full reach. One of the most striking is the giant stellar stream, an arc spanning more than 100,000 light-years, thought to be the remains of a dwarf galaxy swallowed by Andromeda about 700 million years ago. The stars in these streams carry memory. Their chemical fingerprints reveal origins different from the main disk, lower metallicities, unusual patterns, clues that they were born in smaller systems before being absorbed. By mapping them, astronomers reconstruct Andromeda's violent past, a record of cosmic cannibalism. Some arcs loop gracefully, others tangle, overlapping like threads. Simulations show how each one forms. A dwarf galaxy ventures too close. Tidal forces pull its stars into long trails, and the remnant vanishes into the larger host. Over billions of years, Andromeda has repeated this act dozens of times. Its halo is a graveyard of swallowed companions, their ghosts still visible in faint streams. You let the thought settle. The soft oval above your horizon is not only alive with new stars but haunted by the remains of old galaxies. The beauty of Andromeda hides violence, the endless hunger of gravity weaving new light out of shredded systems. Every faint arc is a scar, a testimony that galaxies grow not gently but by tearing others apart. Around all of this, the spirals, the streams, the double heart, stretches something even larger. A halo of gas so vast it dwarfs the luminous galaxy, extending nearly 1 million light-years into the dark. You imagine the oval smear above, and then picture it surrounded by an invisible cocoon, a volume so immense that it overlaps with the halo of the Milky Way itself. The halo is not bright to your eyes. It is almost transparent, discovered only with sensitive instruments. In the 2010s, the Hubble Space Telescope mapped it using background quasars. As their light passed through the halo, it carried fingerprints of absorption, evidence of hot, ionized gas stretching hundreds of thousands of light-years. The numbers astonished astronomers. The halo may hold as much mass as half the stars in the galaxy. An ocean of thin, heated plasma bound by gravity but nearly invisible. Temperatures reach into the millions of degrees, yet the density is low enough that the gas glows only faintly in X-rays and ultraviolet absorption lines. To detectors, it is a shimmering veil. To you, standing under the sky, it is nothing, a silent presence surrounding the blur. And yet, it is there, shaping the fate of galaxies. This halo matters because it is the reservoir. It feeds the disk with fresh gas, fuels star formation, and receives the outflow from dying stars and supernova. the cycle of matter, birth, death, rebirth, extends far beyond the arms into this giant atmosphere. Chemical analysis shows it is enriched with oxygen, carbon, and heavier elements, proof that the halo has been seeded by generations of stellar explosions. Simulation suggests the halo also explains how Andromeda interacts with its neighbours. Its outer edges may already brush against the Milky Way's halo, meaning the two galaxies are not only destined to merge in billions of years but are already touching, invisibly. The local group is a web of halos colliding before the stars themselves ever meet. You let the scale sink in. The oval you see above is 200,000 light-years across, but the halo stretches 5 times farther in every direction. To your eye, it is absence. In reality, it is the galaxy's true size, a structure so immense it bends your sense of proportion. The visible stars are only the core. The halo is the ghost body, the unseen giant that carries Andromeda's weight into the dark. Scattered through that halo are pearls of light, globular clusters, ancient spheres of stars that orbit like satellites, relics of the galaxy's earliest days. You turn your attention to them and see a kingdom suspended in the dark, hundreds of clusters surrounding Andromeda, each one a world of stars bound tightly into a ball. Astronomers have catalogued more than 450 globular clusters in Andromeda, far more than the Milky Way's approximately 150. These clusters are ancient, many over 10 billion years old, nearly as old as the universe itself. Their stars burn faint and red, low in metals, fossils from an era before galaxies have been enriched by generations of supernovae. They are living time capsules, carrying the chemical memory of the first epoch of star formation. The largest of them, Male 2, G1, is a giant even among giants. Located about 130,000 light-years from Andromeda's centre, it contains several million stars and is brighter than any globular cluster in the Milky Way. Its mass is so great that some scientists suspect it is not merely a cluster, but the stripped core of a dwarf galaxy long ago consumed. Inside, stars of multiple ages suggest a complex history, more layered than a simple swarm should be. G1 is a ghost within a ghost, a fragment of another galaxy now serving as a jewel in Andromeda's crown. Other clusters, though smaller, carry their own mysteries. Some lie deep in the halo, so far from the core that their orbits trace vast ellipses. A few may even belong to galaxies now destroyed, captured and repurposed by Andromeda. Each cluster has its own orbit, its own path across the million light-year expanse, like bees circling a hive too vast to see in full. You feel the contrast between scale and intimacy. Each cluster is a dense knot, with stars packed 100 times more tightly than in your neighbourhood of the Milky Way. From inside one, the night sky would blaze with thousands of suns so bright that darkness would never truly fall. Yet from Earth, these same clusters appear as tiny specks, barely visible in long exposures. In the 20th century, astronomers debated the nature of globular clusters. Were they remnants of galaxy formation or the stolen cores of smaller systems? Modern evidence suggests both. Some are pristine fossils, survivors from the dawn of Andromeda. Others are captives, relics of dwarf galaxies absorbed and dissolved. The kingdom is not uniform. It is a patchwork of histories, a gallery of survivors gathered by gravity. Even now, new clusters are found. Digital sky surveys continue to extend the census, revealing faint smudges at the edges of the halo. Each new discovery adds to the sense that Andromeda's empire of clusters is unmatched in the local group. For you staring at the haze above, none of this detail is visible, but within that faint oval hangs a court of globulars, ancient, dense, unyielding, orbiting silently, witnesses to the galaxy's long and violent history. Andromeda's history is written not only in clusters and streams, but in appetite. It has grown by consuming others, swallowing smaller galaxies until their stars became its own. You stand beneath the blur and understand that what looks so quiet is the product of violence repeated over billions of years. The evidence surrounds it. The giant stellar stream mapped in the early 2000s is the clearest trace, the shredded remains of a dwarf galaxy pulled apart less than 1 billion years ago. Its stars loop in long arcs, wrapping the halo in pale ribbons. Chemical analysis shows that their metallicity differs from Andromeda's disk, proof that they were born elsewhere. The galaxy devoured their home and kept the ghosts. Other dwarfs have been less fortunate. Simulations suggest that over its lifetime, Andromeda has absorbed dozens, perhaps hundreds, of small companions. Each merger added mass, stirred the disk, warped the arms. The 10 kiloparsec ring may itself be the scar of such a collision, a resonance frozen into structure. What you see as beauty is also trauma, the mark of impact turned into geometry. The globular clusters tell the same story. Some, like Mayal 2, may be the stripped cores of galaxies once whole. Their stars of multiple ages reveal they did not form in a single burst but carried complex histories. When their outer shells were stripped away, the cores remained, still orbiting, still shining, prisoners turned trophies. Even now, Andromeda is not finished. It still holds more than 30 dwarf galaxies in orbit, M32, M110, and fainter satellites scattered like sparks. Some will survive for billions of years, dancing around the giant. Others will spiral inward, torn apart, their stars scattered into the halo. The process is slow but relentless. Gravity has infinite patience. You feel the chill of that thought. Galaxies do not simply exist, they feed. Growth is not peaceful expansion, but cannibalism. The blur above you is an empire built on absorption, its mass the sum of countless smaller lives. And in billions of years, the Milky Way will be next. Among the survivors of that empire, one stands strangely close. M32, a compact elliptical galaxy that clings to Andromeda's side like a fragment left behind. To your eyes it would appear as a dim neighbour near the larger haze of Andromeda, barely distinguishable without a telescope, but in truth it is one of the strangest and most revealing members of Andromeda's family. M32 is small beyond comparison to its host. Andromeda spans nearly 200,000 light-years across, while M32 stretches only about 6,500 light-years at its widest. Its scale is closer to a single spiral arm of its parent than to a full galaxy. Yet despite its modest size, M32 shines with unusual intensity. Its stars are densely packed, making its surface brightness higher than almost any other dwarf galaxy known. This is why it catches attention in photographs. A tiny glowing oval pressed up against the immense disk of Andromeda. Its structure is what sets it apart. Classified as a dwarf elliptical, DE2, M32 lacks the features we associate with spirals or irregulars. No arms, no dust lanes, no obvious gas clouds. It looks like a smooth, pale ball of stars, as though every irregularity has been rubbed away. For decades, astronomers debated why. The most convincing explanation is tidal stripping. Long ago, M32 may have been a more massive galaxy, with extended arms or at least a larger halo. But as it ventured too close to Andromeda, gravitational tides pulled away its outer layers. Stars were scattered into Andromeda's halo, gas clouds siphoned off. leaving behind only the dense, bright core. What we see today is the fossil of a once larger system. Evidence supports this. M32 contains very little gas. Astronomers describe it as gas poor. Star formation has nearly ceased. The few young stars it holds are outnumbered by billions of old red ones. Its stellar populations suggest bursts of activity in the distant past, followed by silence. Stripped of fuel, the galaxy was quenched. Andromeda's gravity did not just tear at its structure, it stole its future. Still, M32 remains remarkable. At its heart lies a supermassive black hole of about 2 to 3 million solar masses, similar in size to Sagittarius A star in the Milky Way. This nucleus glows brighter than expected for a dwarf galaxy, adding to the idea that M32 is a remnant core. Stars there orbit tightly, some racing at hundreds of kilometers per second around the invisible anchor. The density is extreme. If you lived inside Me32, your night sky would never be dark. Thousands of suns would crowd your vision in every direction, burning too brightly for silence. M32 was recognized early in the history of astronomy. Charles Messier catalogued it in 1764, assigning it the number M32 as one of the first companions of Andromeda he could identify. To him, it was only a fuzzy oval near the brighter smear of M31, easy to mistake for a small comet. Later observations revealed its true nature as a compact galaxy. By the 20th century, studies with larger telescopes confirmed its high stellar density and lack of gas, painting the picture of a stripped elliptical. You feel the tension in that story. What seems at first like a faint neighbour is really a survivor of violence. It is a galaxy reduced to essentials, its outer beauty erased, its gas stolen, its arms ripped away. And yet it persists, orbiting the giant that nearly destroyed it, glowing still with the light of billions of aging stars. To see M32 beside Andromeda is to see the contrast between dominance and survival, the giant that consumes and the companion that clings, scarred but enduring. In modern surveys, M32 remains a subject of study. Astronomers model its past encounters with Andromeda, trying to reconstruct how many times it plunged through the larger disk. Each passage would have stirred waves of star formation, both in Andromeda and within M32 itself, before stripping away more material. Some simulations suggest M32 may even be responsible for the 10 kiloparsec ring in Andromeda's disk, a ripple frozen in place by one of its intrusions. If true, the faint satellite played a role in sculpting the structure of its mighty host. The story of M32 is not just about loss, it is about resilience. Against the gravity of a giant, it has not been completely erased. It holds on to its core, its stars, its black hole. It reminds you that galaxies, like living things, can be battered, reduced, stripped, and still remain. Not far from M32 drifts another companion, softer and dimmer, stretched into an oval haze. M110, the ghostly neighbour of Andromeda. To a small telescope, it appears as a faint smudge just below the main galaxy, an afterthought beside the blaze of M31. But in truth, M110 is one of the most significant satellites, a dwarf elliptical, larger than M32, yet wrapped in an aura of quiet ruin. M110 spans roughly 15,000 light-years, making it more than twice the size of M32, though still a fraction of Andromeda's 200,000 light-year disk. Its shape is diffuse, its light uneven. Unlike the dense brightness of M32, M110 has a mottled appearance, with dark patches that hint at dust. For a long time, astronomers thought dwarf ellipticals contained no dust at all, yet M110 surprised them. In the 1990s, deep imaging revealed faint dust lanes near its centre, evidence that this ghost still holds remnants of the material needed for star formation. Its stellar population is mixed. Most of its stars are old, quiet and metal-poor, glowing red with age. But scattered among them are younger groups, evidence of more recent bursts of star formation. Observations suggest that a few billion years ago, M110 still managed to create new stars, long after many other dwarfs had gone silent. This makes it different from the quenched M32. The ghost has not yet completely faded. The presence of globular clusters adds to its story. Astronomers have identified at least 8 globular clusters bound to M110, small jewels orbiting the faint oval. These clusters mark it as more complex than a simple dwarf. They hint at a history of interactions, perhaps even the remnants of smaller companions now merged into M110 itself. You stand beneath the sky and try to reconcile the faint smear with its reality. This ghostly neighbour contains tens of billions of stars, arranged in a diffuse oval, tugged and distorted by Andromeda's pull. Its light is soft because it is stretched, thinned like smoke across the void. It is less compact than M32, easier to disrupt, more fragile against the tides of its giant parent. History confirms this fragility. Some astronomers believe Me-110 is in the process of being stripped, its outer stars already tugged into Andromeda's halo. Deep surveys in the 2000s and 2010s revealed faint streams of stars near its position, possible debris pulled away by tidal forces. If true, M110 is slowly dissolving, its stars escaping to join the empire of Andromeda. And yet, like M32, it endures. Its dust and younger stars mark it as not entirely spent. It is quieter, dimmer, but not lifeless. Charles Messier himself overlooked it. He catalogued M31 and M32 in 1764, but for reasons never fully clear, he did not add M110. It was only formally catalogued later as NGC 205 before astronomers recognized it as a major companion of Andromeda. In 1967, it was officially added to the Messier list as M110, the last of its entries. For you, standing under the real night, none of this complexity is visible. You see Andromeda as a haze, and just below it, if the air is clear and the darkness deep, a smaller blur. That blur is M110, fragile, ghostly, stretched thin, yet holding billions of suns and the story of survival against a giant. It is a neighbour on the edge of disappearance, a reminder that galaxies live, fade, and sometimes dissolve before your eyes. Beyond M32 and M110, Andromeda commands an even larger court. Dozens of smaller satellites, faint galaxies discovered only in recent decades, sparks barely clinging to visibility on the edge of the giant's halo. You picture them circling unseen, each one a fragment of starlight bound by gravity. Too dim for your eyes, but alive in the depths of long exposures. Astronomers knew of M32 and M110 for centuries, but the true population of Andromeda's companions emerged only with modern surveys. In the 20th century, only a handful were catalogued. Andromeda 1, 2, 3 and 4, faint dwarves scattered around the parent. Their discovery required deep photographic plates because their stars were so sparse and diffuse. Even then, they appeared as little more than barely brighter patches of night. The real transformation came in the 2000s and 2010s. Digital sky surveys, the Sloan Digital Sky Survey, Pan-STARRS, PANDAS, Pan-Andromeda Archaeological Survey began mapping Andromeda's halo in unprecedented depth. With them came a flood of new satellites: Andromeda 9, discovered in 2004, Andromeda 25, added in 2011, Andromeda 32, announced in 2013. By the mid-2000s, the tally exceeded 40 known dwarf companions, and the number has continued to grow. These galaxies are faint beyond belief. Some are ultra-faint dwarfs, with only a few thousand stars, barely distinguishable from the background of the Milky Way. They are the smallest galaxies ever found, on the edge of what counts as a galaxy at all. Their discovery was possible only through statistical analysis, counting excesses of stars in digital catalogues, teasing signal from noise. You let the image form. Andromeda's halo is not empty but speckled with these faint embers. Each one carries its own orbit, its own fragile population. Some are stretched into tidal shapes, already being shredded, their stars peeling away. Others cling tightly, dense enough to resist for now. Together they form a swarm that extends hundreds of thousands of light years, a vast retinue hidden from casual view. The diversity among them is striking. Some, like Andromeda 2, show evidence of past starbursts, with populations of varying ages. Others, like Andromeda 9, are among the faintest known, so dim that they challenge definitions of galaxies. A few seem elongated, distorted by Andromeda's pull, caught in the act of dissolution. In every case they reveal a truth. Andromeda is still building itself, still gathering companions, still sculpting its outskirts through gravity's reach. For you, the thought shifts the blur above your horizon into something richer. It is not just a haze, but the centre of a kingdom, with dozens of faint satellites, most invisible, some already dying, all orbiting the giant that will decide their fate. The oval above is not solitary. It is surrounded, accompanied, followed by a retinue of galaxies too faint for your eyes, but real, patient, and doomed to join the larger whole. Together these companions form more than a crowd. They are a family, a miniature cosmos orbiting Andromeda, reflecting the laws by which galaxies grow and survive. You raise your eyes toward the haze, and though you cannot see them, you know that around it swarm M32, M110, and dozens more, each one following its orbit in silence, each one part of a greater pattern. This system is not random. The satellites are arranged in structures. In the 2010s, astronomers discovered that many of Andromeda's dwarf galaxies are aligned in a thin plane, stretching across hundreds of thousands of light years. Instead of forming a chaotic cloud, they orbit like dancers in a flattened sheet. The cause is debated. Perhaps they were accreted together from a single group. Perhaps tidal forces aligned them. Perhaps the plane is temporary and will dissolve. But its existence shows that satellite systems can be far more ordered than once thought. The variety among them offers a living laboratory. M32 is compact and stripped. M110 is diffuse and ghostly. The ultra-faints are fragile wisps. Others are denser, with histories of multiple starbursts. By comparing them, astronomers test theories of galaxy formation, how dwarfs evolve near giants, how gas is lost, how dark matter shapes their survival. Each satellite is a clue, and Andromeda provides dozens, more than the Milky Way currently reveals. You let the thought expand. To stand beneath Andromeda's blur is to stand before a model of cosmic structure itself. One giant galaxy at the centre, surrounded by smaller ones, each orbiting, some merging, some dissolving. This is not only the story of Andromeda, it is the story of the universe. Clusters of galaxies orbit larger clusters, groups orbit superclusters, and the pattern repeats across scales. Andromeda's family is a miniature cosmos, a mirror of the greater web. The future will fold them together. Many of the dwarfs will not survive the next few billion years. They will be torn apart, their stars joining the halo, their clusters adding to the empire of Andromeda. Some may endure, orbiting within Milkomeda after the merger with the Milky Way, relics inside the new giant. In either case, their role is written. Companions now, fossils later. For you, the knowledge adds weight to the faint smear you see tonight. It is not a solitary galaxy, but a system with its own court, its own satellites, its own history of family and loss. The blur above your horizon is both present and future, a picture of how galaxies live not alone but in company, bound together, destined to merge, destined to change. Long before astronomers proved that Andromeda was a galaxy, it was simply a mystery on the sky, a faint cloud noticed by careful watchers, puzzled over by early telescopes, and scribbled into catalogues as a curiosity. You stand beneath the same sky now, and the haze above you is unchanged, yet it has carried human questions for more than 1,000 years. The first clear record comes from the 10th century. In the year 964 CE, the Persian astronomer Abd al-Rahman al-Sufi published his Book of Fixed Stars. Working in Shiraz, far from city lights, he described a little cloud in the constellation of Andromeda. His text and illustrations remain among the oldest preserved references to the object we now call M31. To him, it was not a galaxy. That word did not exist. It was simply a patch, unlike the stars that glittered sharp and clean. His language was practical, yet it captured the oddness, a persistent smudge, not moving like a comet, not sharp like a star, something in between. For centuries his note stood alone. Medieval Islamic scholars copied his book, and through translations it influenced European astronomy. The cloud became part of inherited star lore, a marginal entry compared to planets and constellations, but present all the same. When you tilt your head back tonight, the blur you see is the same one al-Sufi marked more than a millennium ago. By the 17th century, telescopes had entered the scene. In 1612, the German astronomer Simon Marius turned one of the new instruments on Andromeda. His description is famous, like a candle shining through horn. To his eye, magnification revealed not sharp points but a diffused glow, as though a flame were dimmed by a translucent shell. The metaphor is strange but precise. A candle through horn is brighter than smoke, dimmer than glass, something seen but not clearly. His words caught the paradox. The telescope made Andromeda brighter, but it refused to resolve into stars. In the same century, Galileo had already used his telescope to dissolve the Milky Way into stars, proving that its haze was countless suns. If Andromeda had been part of the Milky Way, observers expected the same, yet even under magnification it stayed smooth, featureless, stubborn. This contrast deepened the puzzle. Over 100 years later, the French comet hunter Charles Messier took up the haze. In 1764, he added it to his catalogue as M31. His goal was not to explain it, but to list objects that might confuse comet searchers. Andromeda, like many nebulae, was an annoyance to him, a patch that could be mistaken for a discovery but was not. Ironically, his effort to avoid mistakes preserved the record for future generations. M31 became fixed in astronomical literature, a label waiting for deeper meaning. Through the 18th and 19th centuries, Andromeda was photographed, charted and debated. In 1850, William Parsons, the third Earl of Rosse, used the Leviathan of Parsonstown, the largest telescope of the time, to sketch spirals in other nebulae. Andromeda itself showed hints of structure, elongated with dark lanes that hinted at depth. Astronomers began to call it a spiral nebula, one among many, yet the name meant little. Was it a cloud in the Milky Way forming new stars or an entire system outside? Nobody knew. You picture the generations passing, scholars copying Al-Sufi's manuscript by lamplight, Marius squinting through glass ground by hand, Messier scanning the Paris sky for comets, jotting down the oval as a nuisance, 19th century observers straining at giant telescopes, glimpsing swirls in the blur. Each left a trace, and all of them together built the foundation. The blur above you is not just light from a trillion stars, it is also the weight of human memory, of 1,000 years of eyes that puzzled, compared, and recorded. Tonight, when you notice it, you're part of that chain. By the dawn of the 20th century, the blur of Andromeda had become more than a curiosity. It was a battlefield of ideas, the subject of one of astronomy's greatest arguments, the Great Debate of 1920. You look up at the haze tonight and see only a faint patch, but a century ago that patch carried the weight of the universe's scale on its shoulders. At the time, two astronomers embodied opposing visions. Harlow Shapley, studying globular clusters, believed the Milky Way was staggeringly large, perhaps 300,000 light-years across, and that everything in the sky, including the spiral nebulae, was part of this vast single system. To him, Andromeda was no more than a cloud inside the Milky Way, a local object in a giant galaxy that already encompassed the cosmos. Heber Curtis, on the other hand, argued that these spirals were not nebulae at all, but island universes in their own right, galaxies as big as the Milky Way lying far beyond it. The confrontation climaxed on April 26, 1920, at the Smithsonian Institution in Washington, D.C. The event was framed as a debate, but in reality it was 2 long lectures delivered to a hall full of astronomers. Shapley laid out his vision first. He emphasized his recent work on globular clusters, showing how they outline the Milky Way's size and our offset position within it. He painted the galaxy as immense, and in such immensity there was no need for other galaxies. Curtis countered with evidence of novae in Andromeda. The most dramatic was the nova of 1885, which had flared so brightly within the haze that it could be seen with the naked eye. If Andromeda were inside the Milky Way, such an event should have been impossibly faint. Its brightness suggested instead that Andromeda was at an enormous distance, hosting stars in quantities comparable to the Milky Way. He also pointed to the appearance of spiral structure. If Andromeda were only a nearby gas cloud, why would it mimic the world form of a galaxy? The audience listened, intrigued but unconvinced either way. Both men carried authority. Both had data. Yet their conclusions contradicted each other completely. Shapley had overestimated the Milky Way's size, while Curtis had underestimated it. But Curtis was closer to the truth in placing Andromeda outside. The debate ended without a winner, leaving the oval haze still undefined, its identity suspended between 2 worldviews. You can almost feel the tension of that evening. 2 men on stage, voices echoing in the Smithsonian's hall, one insisting the Milky Way contained everything, the other daring to say it did not. For the audience, the stakes were enormous. To agree with Curtis was to abandon centuries of belief that the Milky Way was the universe itself. To follow Shapley was to ignore growing evidence that the spirals were galaxies of their own. The smudge above your horizon was the battlefield where the universe itself was being argued over. The The newspapers called it the Battle of the Universe. Articles appeared in the New York Times and other outlets describing how scientists clashed over the very size of existence. Ordinary readers could not follow the technicalities, but they sensed the drama. The cosmos might be small and local, or vast and filled with other Milky Ways, and the deciding clue rested in the faint oval of Andromeda. Curtis also emphasised the distribution of spiral nebulae. Thousands had been catalogued by then, spread evenly across the sky. If they were inside the Milky Way, why were they not clustered along the galactic plane like stars and gas clouds? Their even distribution made sense only if they were external, scattered across the universe. Shapley replied that dust and absorption in the Milky Way could explain the patterns, but his defence felt strained. For months afterward, the debate reverberated in journals and meetings. Neither man conceded. Observers continued to take sides. Andromeda itself remained a blur, silent above them, waiting for better instruments to deliver the answer. For you standing beneath the sky, the outcome is obvious. You know the haze holds 1 trillion suns, a galaxy in its own right. But in 1920, the question was still alive, uncertain, even dangerous to reputation. The great debate was not resolved that night, but it prepared the ground. Within 3 years, Hubble's discovery of Cepheid variables in Andromeda would settle the matter once and for all. The answer came with glass plates, patient nights, and the sharp eye of Edwin Hubble, who turned the world's largest telescope toward the blur of Andromeda and found a rhythm of stars that carried the scale of the universe. You follow him in 1923 climbing the mountain road to Mount Wilson Observatory in California, where the 100-inch Hooker telescope stood beneath the dome like a giant eye waiting to open. The Hooker telescope was the greatest instrument of its age, its mirror gathering more light than anything built before. Hubble, restless and meticulous, used it to study the nebulae. Night after night he exposed glass plates, thin rectangles coated in emulsion, waiting hours as the faint light of Andromeda etched itself into them. Each plate looked at first like scratches and dust, but when compared over time, points of light betrayed their secrets. In October 1923, Hubble noticed one of those points changing. At first he marked it N for nova, but the brightness did not match a nova's sudden flare. Instead, the star pulsed, dimming and brightening with a steady beat. Hubble recognized it for what it was, a Cepheid variable. Cepheids were already known to be cosmic yardsticks. In 1912, Henrietta Swan Leavitt had discovered the law that bound their period to their luminosity. The longer the pulsation, the brighter the star truly was. By measuring the period, one could know the intrinsic brightness, and from the difference between that and the apparent brightness, calculate distance. Leavitt's law transformed flickering stars into rulers of the cosmos. Hubble applied it to the star in Andromeda. The numbers leapt beyond expectation. This Cepheid was not hundreds or thousands of light-years away. It was nearly 1 million light-years distant by his first calculation. Later refinements doubled and then more than doubled that figure, placing Andromeda at about 2.5 million light-years. But even the earliest result was enough. The haze was outside the Milky Way. It was a galaxy on its own. In 1924, Hubble announced his results. The great debate was over. Curtis's vision of island universes was confirmed. Shapley's vast Milky Way was reduced to a single galaxy among billions. The scale of the universe had exploded. Humanity's home had shrunk from the cosmos itself to just one spiral in a sea of spirals. You stand under the same haze tonight and feel the echo of that shock. For centuries, the Milky Way had been everything. In a few calculations, that certainty collapsed. The faint blur above your horizon became the doorway to a universe without edges. Hubble did not stop with Andromeda. He measured Cepheids in other spirals, M33 NGC 6822, and built the first reliable distance ladder beyond the Milky Way. Soon, maps filled with galaxies. The term nebula gave way to galaxy, and the cosmos grew from one island to an ocean. For the scientists of the 1920s, it was a revolution. For you, a century later, it is the background of ordinary thought. Of course, the universe holds galaxies. But remembering that it was Andromeda, this faint haze that first carried the proof restores its strangeness. That blur is not just light from a trillion stars, it is the place where the universe expanded in the human mind. A century after Hubble's breakthrough, the same galaxy has become not just a proof of scale, but a laboratory of detail. Modern surveys with Hubble, Gaia, and other instruments have resolved Andromeda into individual stars by the millions, turning the blur into a map more intricate than any ever drawn of another galaxy. You stand under the same faint oval tonight, but behind its haze are catalogues so vast that they hold more than you could count in a lifetime. One of the greatest of these efforts was the panchromatic Hubble Andromeda Treasury, PHAT, conducted in the 2010s. Using Hubble's sharp eyes, astronomers stitched together more than 400 individual images, covering a third of Andromeda's disk. The result was a mosaic of over 100 million resolved stars, each one plotted with precision. For the first time, another galaxy beyond the Milky Way was mapped in such detail that scientists could study its stellar populations, almost as if they were local. The PAT survey revealed the life cycle of stars written into Andromeda's arms, blue clusters glowing with new light, red giants marking ancient generations, and pockets of gas glowing in H2 regions. It showed that star formation was not uniform but patchy, clustered, sculpted by density waves in the spirals. The project became a cornerstone for understanding how galaxies sustain themselves across billions of years. At the same time, the Gaia spacecraft, launched in 2013 by the European Space Agency, measured the positions and motions of more than 1 billion stars in the Milky Way, but its reach extended into Andromeda too. Gaia's sensitivity allowed astronomers to chart the motions of Andromeda's stars and companions, refining predictions of its future collision with the Milky Way. For the first time, humanity had a dynamic map not only of its home galaxy, but also of its nearest giant neighbour. You let the scope of that achievement press down. What once was a smudge in Al-Sufi's manuscript is now a catalogue where every star is a data point, every motion tracked. The blur has become a database, vast enough to overwhelm imagination. Other surveys added more. The Pan-Andromeda Archaeological Survey, PANDAS, mapped its halo, uncovering tidal streams and faint satellites. The Chandra X-ray Observatory studied its hot gas, while the Spitzer Space Telescope traced its dust. Together they built a layered image: visible light, infrared, ultraviolet, X-ray, each wavelength adding to the portrait. The result is not only beauty but utility. Andromeda has become the model by which astronomers test their theories of galactic evolution. It is close enough to resolve, yet large enough to represent a true spiral system. By comparing it to the Milky Way, scientists learn what is typical and what is unique. By measuring its stars, they test models of stellar evolution. By charting its halo, they probe dark matter. For you, looking up tonight, the haze is unchanged. But in truth, it is the most studied galaxy beyond the Milky Way, the first to be mapped star by star, the first to show us what another great spiral looks like in living detail. The oval above your horizon is not just a neighbour, it is a mirror, a laboratory, and a promise of what our instruments will uncover when turned to more distant galaxies in the centuries to come. Andromeda is not only a neighbour, it is a mirror. To understand our own galaxy, we compare it to this twin across the void, measuring similarities and differences until both begin to make more sense. You lift your eyes to the faint oval and recognise it not just as another galaxy, but as a reflection that shows what the Milky Way might look like if you could step outside it. The two are alike in many ways. Both are barred spirals, their disks threaded by sweeping arms, their centres housing supermassive black holes. Both are dominant members of the local group, surrounded by swarms of dwarf galaxies. Both stretch across hundreds of thousands of light years, massive enough to bend the orbits of companions and shape the gravitational field of their neighbourhood. To imagine one is to glimpse the other, yet the differences are telling. Andromeda is larger, about 200,000 light-years in diameter, compared to the Milky Way's 100,000 to 120,000. It likely holds nearly 1 trillion stars, twice the Milky Way's 400 to 500 billion. Its halo is also more extended, stretching up to 1 million light-years, overlapping already with our own. In mass, estimates put them close, but most analyses give Andromeda the advantage, weighing in at 1.1 to 1.5 trillion solar masses versus the Milky Way's approximately 1 trillion. The structures inside show contrast too. The Milky Way's spiral arms are asymmetric, patchy, with gaps partly hidden by dust. Andromeda's arms, while also irregular, show long dust lanes cutting across, visible because the galaxy tilts toward us at about 77 degrees. Our own galaxy is harder to map from within. Andromeda gives us the external view. Cores differ as well. The Milky Way's Sagittarius, a star black hole, weighs about 4 million suns. Andromeda's central black hole may be 100 to 200 million suns, more than 20 times heavier. Its nucleus is split into 2 peaks of light, a double heart, unlike the single bright core of the Milky Way. Where ours is modest, Andromeda's centre is strange and oversized. You let the comparison settle. To look at Andromeda is to see both a sibling and a rival, a galaxy built on the same blueprint but scaled up, heavier, stranger in its heart. The Milky Way is not unique. It is one of 2 great spirals bound together, already in the first steps of the future merger. For centuries, we could not see the Milky Way's structure from inside it. Dust and perspective hid its true shape. But Andromeda gave us the vantage point. By studying its arms, clusters and halo, astronomers learned what features to expect in our own. By contrasting the two, we discovered what galaxies share and where they diverge. The faint oval above you is not only an object of wonder, it is a mirror, showing you both the likeness and the difference, reminding you that the Milky Way is not alone and not supreme. What makes Andromeda truly massive is not just the stars you see, nor the gas and dust that glow in telescopes, but the invisible weight of dark matter, an unseen halo that outweighs the light. You lift your gaze toward the faint oval and know that what your eyes cannot see is the bulk of its substance. Astronomers uncovered this truth in the 20th century, when they measured the rotation curves of galaxies. In theory, stars far from the centre should orbit more slowly, just as planets move slower the farther they are from the Sun. Gravity weakens with distance, yet when radio telescopes traced the speed of hydrogen gas in Andromeda's outer disk in the 1970s, they found something shocking. The rotation curve stayed flat. Stars and gas far from the centre moved as fast as those closer in. The visible mass was not enough to explain the motion. The implication was unavoidable. Andromeda is wrapped in a dark matter halo. a sphere of invisible material extending far beyond the luminous disk. This halo holds far more mass than the galaxy's stars, gas and dust combined. Without it, the outer regions would fly apart. With it, they remain bound, the invisible hand of gravity keeping the trillion suns in place. Estimates suggest that dark matter makes up more than 80% of Andromeda's mass. The luminous galaxy, the spiral arms, the glowing clusters, is only the tip of the iceberg. The true Andromeda stretches much farther, 1 million light-years across, defined not by light but by gravity. When you look at the blur, you're seeing only the centre of a far larger body, most of it hidden. You feel the dissonance of that thought. A galaxy is supposed to be light, stars burning across time, but the weight is elsewhere, in something unseen, something we still cannot identify. Dark matter does not shine, does not absorb, does not scatter photons. It reveals itself only through motion. Andromeda's flat rotation curve is a signature written not in light, but in speed. Comparisons to the Milky Way deepen the picture. Both galaxies require halos of dark matter to explain their structure, but Andromeda's appears even more massive, perhaps 1.1 to 1.5 trillion solar masses in total. Some studies suggest its halo extends farther, overlapping with the Milky Way's. In this view, the two galaxies are already touching, not in stars but in dark matter. Their future merger is only the visible end of an invisible union that has already begun. Modern surveys sharpen the outline. The PANDAS survey mapped faint streams in Andromeda's halo, tidal remnants that trace the dark matter's pull. Satellite galaxies orbit within this hidden field, their motions betraying the distribution of mass. Simulations show that without dark matter, these companions would long ago have drifted away. Instead, they circle, locked in a web we cannot see. For you, the haze above is deceptive. It looks small, fragile, a faint smear. Yet its true body is colossal, built not from stars but from shadows. Dark matter defines the galaxy's size, its shape, its history. The spirals, the clusters, the streams, all are embedded in that unseen architecture. This realization reshaped cosmology. Andromeda is not unique. Every galaxy carries the same secret. But because Andromeda is close, because we can trace its stars in detail, it became one of the best laboratories for studying dark matter halos. By measuring its motions, mapping its streams, and modelling its future, astronomers test theories of what dark matter might be. Particles beyond the standard model, cold relics of the early universe. The galaxy becomes not only a mirror for the Milky Way but a probe of fundamental physics. You let the thought weigh on you. The oval above your horizon is both presence and absence. Its stars shine, but its mass is hidden. Its light is fragile, but its gravity is immense. To see Andromeda is to be reminded that most of the universe is invisible, that the cosmos is made more of shadow than of fire. Andromeda is more than a neighbour or a mystery of dark matter. It is both a key to understanding how galaxies evolve and a reminder of your own place beneath the sky. You raise your eyes to the faint oval and realise it has served as a laboratory for science and a mirror for human thought. Because Andromeda is close enough to resolve into individual stars, it became the first spiral galaxy studied almost star by star. Surveys like FAT in the 2000s mapped more than 100 million of them, showing clusters of different ages, from newborn blue stars in H2 regions to red giants billions of years old. With these maps, astronomers reconstruct how the galaxy grew. Bursts of star formation, streams of stars from swallow dwarfs, and the slow building of its halo. Every faint star plotted is another clue in the biography of a galaxy. Its tidal streams, uncovered by pandas, prove the theory of hierarchical growth, that large galaxies are built from smaller ones. Arcs and loops in the halo are fossils of mergers, each the remnant of a system torn apart. They show that galaxies are not steady islands, but restless builders, recycling stars into new shapes. And because Andromeda approaches the Milky Way at 301 kilometers per second, it also offers a preview of our future. Simulations show how the two giants will collide in 4 billion years, their spirals stretched into long tails, their cores spiraling into one. By watching Andromeda now, we watch the script of our own galaxy's fate unfold. But the lessons do not stop with astrophysics. For you, standing beneath the night, Andromeda is also a personal reminder of scale. That blur contains perhaps 1 trillion stars. If even a fraction host planets, there may be trillions of worlds inside that haze, landscapes, skies, oceans you will never see. The weight of that thought presses down,